Hi Ms. Balch, welcome to me and Anna's video about thermodynamics. In this video I do have a couple of special guests on my part, and that does include the one and only Craig Duran and Scooter Duran, which can be seen here. So in our video for the first half we talked about pressure, STP, the ideal gas processes, PV diagrams including constant temperature, constant pressure, and constant volume processes, and we went over what that means and what some of those look like on the actual PV diagram. And then Anna will talk about adiabatic processes, heat transfer, and all of that good stuff. So welcome to our video. I hope you enjoy. We had a lot of fun making this. So starting off with pressure. Pressure is the constant microscopic collision of molecules within a gas. The force of pressure at the area in which it's acting is proportional, therefore we can define the ratio of force and area as pressure, with P is equal to force over area. For example, when my brother makes me mad, how much force do I have to put on the area of his head to make it explode, to add enough pressure to make his head explode? To define pressure, we use the unit of pascals. One standard atmosphere, or 1 ATM, is defined as 101,300 pascals, or 101.3 kilopascals. Based on our ability to relate gas pressure to other variables, we know that pressure should be proportional to the temperature of the gas, should be inversely proportional to the volume of the container, and should be proportional to the number of gas particles. 1 ATM pressure and 0 degrees Celsius are known as the standard temperature and pressure, also known as STP. This is a common reference point for many gas processes. When we talk about ideal gas processes, we know that the quantity of the gas is fixed in all processes for the purpose of our calculations, and that the initial values of pressure, volume, and temperature are defined as P initial, V initial, and T initial. The final values of pressure, volume, and temperature are defined as P final, V final, and T final. Processes with the properties listed above are known as ideal gas processes, so it's easier for us to calculate. In this case, the ideal gas law can be written as PV over T is equal to NR, which is the constant, and P final times V final times T final is equal to P initial times V initial times T initial. So earlier we talked about the proportions of gas to volume, pressure, and temperature, and we can use PV diagrams to represent these ideal gas processes, and each point on a PV diagram represents a unique part of the state of gas. There's 3 different types of PV diagrams, with the first one being the constant pressure process, which is also known as the isobaric process. So with an isobaric process, you know that the external pressure and the internal pressure of the gas are equal, and as long as the external pressure doesn't change, the pressure inside won't change either. The next type of PV diagram is the constant volume process, also known as the isochoric process. So when you raise the pressure of a gas without changing its volume, you have a constant volume process. On the PV diagram, it'll appear as a vertical line, so straight up and down in that diagram. And lastly, we have our constant temperature process. It's also known as the isothermal process. And for example, if you have a piston being pushed up and down to compress a gas, but the cylinder holding the gas is submerged in a liquid that is held at that constant temperature, as the gas is compressed, the heat energy transfer allows for the gas to be held at the same temperature as the liquid. To reverse the process of this, you can expand the gas and you won't have that constant temperature process anymore. So you have these 3 different types of PV diagrams that all represent the proportionalities of gas to the pressure, volume, and temperature.
Hi everyone, now that we've covered pressure and all there is to know about that, we're going to move into heat. So adiabatic processes, thermal expansion, specific heat and transformation, and heat transfer. Okay, the first topic we're going to cover is adiabatic processes. Adiabatic processes are when a transfer of energy occurs, but only in the form of work, and basically no heat is transferred throughout the system. The reason for this is because the equation for heat is mc delta T, which means the mass times the temperature times the specific heat, and when the mass and temperature change inversely, there is no change in heat. An example of this would be the vertical flow of air in our atmosphere. So as the air expands and cools and then falls and heats up at the same time, it's inversely changing, so there is no change in heat, just work. Which doesn't mean that there's no temperature change, it's just through the form of work. The next thing we're going to cover is thermal expansion. Thermal expansion is the tendency of matter to change its shape, area, or volume in the response to a change in temperature. There are 2 types of thermal expansion. There is volume expansion and then there is linear expansion. The equation for volume expansion is the change in volume equals the coefficient of volume expansion times the initial volume times the change in temperature. The same thing goes for the linear expansion, except you replace the coefficient of volume expansion with the coefficient for linear expansion. The next thing we're talking about is specific heat and phase changes. So a substance's specific heat is how much heat it requires to change 1 kilogram of that substance's heat up 1 Kelvin. So however much heat it requires to raise that temperature up 1 Kelvin is that substance's specific heat. The symbol for specific heat is C. Phase change is characterized by a change in internal energy without a change in temperature. So a phase change will never occur at the same time as the temperature is being changed. The temperature at which a solid becomes a liquid is its melting point, and the temperature at which a liquid becomes a solid is its freezing point. The temperature at which a liquid becomes a gas is called a boiling point. A good example of a phase change is when water turns into ice in your freezer. And that's it. There are two types of heat transformation. There is heat of fusion, LF, which is the transformation from a solid to a liquid, or a solid and a liquid. And then there is heat of vaporization, LV, which is the transformation between a liquid and a gas. There are three forms of heat transfer, the first being conduction. So that is the transfer of energy or thermal energy directly through a physical material. So if you were to put a pot on the stove is touching the pot and heating it up, or if you were to touch the stove, which you probably shouldn't do, that is conduction. Another form of heat transfer is convection. So a good example of convection is when you boil a pot of water, because convection is the transfer of heat through a fluid. So when the water at the bottom becomes hot, it becomes less dense and it rises to the top and replaces the water that was previously at the top and was more dense and colder, which now is going to go to the bottom. The third form of heat transfer is radiation, which is not happening right now because it is 8:30 p.m. But if we're in the daytime, radiation will be coming from the sun and either heating up me or anything surrounding me. Okay, lastly I'm going to talk about our lab. So for our lab, we chose one that's going to represent the first law of thermodynamics. So PV equals nRT. And what you're going to do is you can take a water bottle of any kind, a container to put the water bottle in, a balloon, and then hot water. And what you'll do is you'll put the balloon on top of the water bottle, put it inside of the container, and then as you dump the hot water into the container, it's going to heat up the air inside of the bottle, which will increase the pressure because of the first law of thermodynamics, and it will blow up the balloon. And that's it. Thanks for watching our video on thermodynamics, and I hope you guys learned something.